My dudes, my dudettes, I am Bins, and welcome to episode 7 of the BRESTMAM series.
What do you mean, Bins? Have there been 6 episodes before this one?
Yes, and you should go watch them if you haven't. The link to the entire playlist is in the description. What? Alright, you got me. I couldn't help myself, okay? I've been messing with the machine between the previous video and this one. Come on, don't give me that look. Let him or her who is without sin cast the first stone, okay?
What have you been doing with this machine, Bins?
Well, I've been exploring the concept of randomness, to be honest, and I went a bit loco with it. A bit cray-cray. A bit... Firstly, I devised a system in which the color of the 5th layer shape, right here, would be truly random, except it'll always be a color that's effectively found in the target shape. The color isn't allowed to be gray nor white, so if those happen to be the only colors in the target shape, then this default dark purple will be chosen instead. Then I thought, why stop there? So I went ahead and added randomness to this base layer code shape as well. Also here, 4 non-gray colors are extracted randomly from the target shape, and those will be guaranteed to be 4 different colors if those are available. If there are only 3 colors in the target shape, then the color of the top layer will be the same as the first. If there are only 2 colors, then they will alternate. If there's only 1, it'll alternate with white, except if the only color happens to be white, then it'll alternate with default dark purple again. And then I thought, why stop there? So I added a splash of randomized color to the smell type code shape as well, based on the same criteria, of course. And then I thought, why stop there? So I explored whether I would be capable of creating a setup that would produce a random target shape that would be guaranteed to include floating layers and optionally smelted bits, so that I could then feed that to the machine for it to figure out and produce. So I went ahead and added that as well. And while I was at it, I also created this selector button so that when you put the factory in buffer mode for leveling up, you can select the amount of buffers. And then I thought, why stop there? So I added a functionality with which, when the machine runs in auto mode, meaning from now on that the target shapes for the factory to produce can, in fact, be truly randomized, while the current shape is being produced, the next shape will already be lined up, sent to the decoder, get analyzed, and then queued. And that allowed me to add this up next display, which, as a fun gimmick, won't be lit if you disable auto mode. Let me show you. So we're gonna disable auto mode, and boom, the display right here gets disabled. And now if I enable auto mode again, whoop, there it is again. You can also click for the next auto shape, except when this thing lights up red. So let's let it search for a while. There we go. Now it's found the next shape, and now I can click the button and this shape will be produced instead. And the machine will automatically load a new one, and it will be completely random. There we go. So yeah, I'll admit I went a bit overboard with the entire thing. Now, I did have a lot of fun, and I'm still contemplating whether perhaps I should do some videos about how all of these randomness features work, but I'm not yet sure. Maybe you'll let me know in the comments if that's something you'd be interested in seeing. Anyway, with these public service announcements behind us, we can get back to our actual story. So we ended last episode having explained how the RTC, the round-trip cycler, how it works, and how the RTC is the key component to a seamless brute force decoder that knocks the previous decoder out of the ballpark. And now the next thing I want to look at with you today is this little thingy tucked away all the way to the top left of the decoder. That part is the float type filter. It determines, based on the target shape, which float types are worth checking and which aren't. The ones that don't make the cut are emitted from the pool. Now, I've had some help with this, and I don't want to go into exact details, but it roughly comes down to the following. If a layer pair is stable, then we won't check that flow type, except if there is an unstable layer pair below it. That is roughly how the filter works. So we discussed how the round-trip cycler works, and also how the translation tables work. The translation tables provide codes that symbolize the cycle lengths of the individual flow types. But now, the flow type filter will block those flow types that don't make sense checking for the particular shape we're trying to decode. So the blocked flow types don't get loaded into the round-trip cycler, reducing the overall cycle time and thus speeding up the machine wherever possible. Then, in the bottom left corner, right here, the flow type code shapes are sent into a lane sorter so that they are neatly lined up, and then the set of selected flow types is loaded into this cycler. This one receives the pulses from the RTC at the exact moments it's supposed to get them, so that the flow types can switch with tick precision. From there, we have another cycler array that I call the layer pulse generator. And in order to explain what it does, let's move here. Let's say this is our target shape, all right? If that's our target shape, then these would be the layers of the corresponding 6 flow types, okay? Now, let's say we want to check the floating pieces in flow type 1. What the layer pulse generator is gonna do is emit pulses whenever the quadrant on a specific layer switches. Now, maybe flow type 1's a bad example, so let's do flow type 2 instead. Flow type 2 covers layers 2 and 3 of the shape. All right? And now, let's look at this for a bit. You can see that whenever the green quadrant switches, the second display from the left lights up. Whenever the blue quadrant switches, the third display lights up. And the problem here is, like you can tell, that the pulse intervals for the green and the blue layer are different. And again, we are dealing with a scenario of multiplication. If we check for flow type 2, then the second display needs to pulsate on every iteration. But the third display only needs to pulsate when we've exhausted the candidates on the layer below it. In this case, layer 2, the green layer, right? This means, in practice, that we multiply the interval for the upper layer with the amount of quadrants on the lower layer. In this case, the green layer has 2 quadrants, and therefore the blue layer needs to switch every 2 steps. If the green layer had 3 quadrants, then the third display would have to light up every 3 steps. Are you with me? And again, this gets slightly more complex as we move into trifloat territory. For flow type 4, it's the bottom layer that needs to pulsate every time. The second layer coincidentally needs to pulsate every time as well, but only because the first layer has only 1 quadrant. If it had 2, then the second display would require a pulse every 2 steps again. All right? And now the third display, well, the interval there equals the amount of quadrants on layer 1 multiplied by the amount of quadrants on layer 2. So if layer 1 did have 2 quadrants and so did layer 2, then the layer 3 display would only get a pulse every 4 steps. Now it gets a pulse every 2 steps. All right? Are you with me on this? Because the thing is, at the current point in our decoder story, we don't have this yet, right? We still need to generate that. But in a very similar way as with our entire RTC story, the round-trip cycler, we want to make the switchovers here completely seamless. So just like with the RTC, the layer pulse generator is yet another intermediary pulse generator that will let us achieve that goal. So if we move back to the actual decoder, then this is the part that's in charge of that. The layer pulse generator itself consists of 6 miniature cycler arrays, one for every flow type. And into each of these 6, I load up the coded values for the quadrant counts. These cyclers are essentially the same ones as the ones we saw in the previous episode, except they're a lot smaller. And the values we need to load up here, well, they come from the translation tables. We do have the tools we need, but now we just need to be careful about which codes go where. Have a look. We have 4 lines, one for each layer of the target shape. And we've got 6 flow types. So for flow type 1, on line 1, we need a pulse on every step. On line 2, the frequency needs to equal the amount of quadrants on layer 1 of the shape. So on line 2, the frequency needs to equal A. Alright? For the second flow type, our base layer is 2. So in that case, it's going to be line 2 that pulsates every step, and line 3 at the interval of the amount of quadrants on layer 2, which is B. And the third flow type, which has base layer 3, it's line 3 that'll pulsate on every step, while line 4 has a pulse for the amount of quadrants on layer 3, right? Now, flow type 4, base layer 1 again, so a pulse for every step on line 1. Then, value A for line 2, and now for line 3, we get the product of the layers below. So on line 3, we load up the value A times B. For flow type 5, it's the same principle, but the top 3 layers. A pulse with every step on line 2, a pulse that equals value B for line 3, and value B times C for line 4. And then flow type 6, finally, we've got base layer 1 again, so an E for line 1, A for line 2, A times B for line 3, and finally, a value that corresponds to A times B times C for line 4. Now, in similar fashion as with the RTC's translation tables, also here, I tried to compress my setup and not do any duplicate work. For example, you can see that in flow type 4, we need line 2 to pulsate with frequency A. But I already made a cycler for that for flow type 1. So instead of creating 2 cyclers, I actually create a single one that will trigger in both of these cases. Well, actually no, in these 3 cases. And the same thing happens here. And the same thing happens here. So actually, while I said I built one cycler array for each flow type, that's actually not true. Instead, there is one cycler for every unique value that we need to get. A, B, C, A times B, B times C, and finally, A times B times C. And those 6 cyclers cooperate where necessary to provide every line with pulses at exact intervals for any given flow type and input shape. Then, those pulses are fed into a quadrant cycler, the likes of which are pretty identical to the BRESTMAM's decoder, and from here on out, the workings are actually pretty much in line with the previous machine. The quadrant cycler outputs code shapes, they get converted to actual shape quadrants, we build floating pieces with them, sort them according to their base layers, and combine them, then calculate a reminder, feed everything into a brute force validation module that accounts for the 9 stacking scenarios that we've already talked about. Okay? Now, whereas the addition of the RTC constitutes the biggest leap forward in reducing the required decoding time, I once again thought to myself, why stop there? And I decided to muscle up and put this decoder on steroids. Because what we see here is actually not just one decoder, it's 3 of them. Here is the main one, the one we've been talking about so far, but then there's also 2 auxiliary decoders. The 2 secondary decoders are in charge of cycling through a reduced set of candidates as a kind of short track to see if a solution can be found early. More specifically, this one will exclusively cycle through trifloats, in other words flow types 4 and 5, while this one will only consider quad floats or flow type 6. If they've exhausted their options, they will simply cease operation and leave the work to the main decoder. And with this approach, virtually any shape can be decoded within roughly 5 seconds. I found a handful of exceptions that take longer, but honestly, I don't think there are all that many. The output lines of the 3 decoders then meet up in this section and will adhere to the principle of first come, first served. If any one decoder finds a solution, it will immediately shut the door for both itself as for the other 2 decoders. Now, I still had some puzzling to do to find a conflict-free setup for cases where different decoders would find a solution either in exactly the same tick or otherwise very, very close to each other so that the trapdoors wouldn't get shut in time, stuff like that. But all in all, it wasn't as much of a hassle compared to the previous accomplishments. Now, before we end this video, there's one last thing I want to show you, and that's the trapdoor mechanism I've used. Props and a shout out to FatCatX for showing me this. So here's what it looks like. If you have a wire with rapidly changing values, then this mechanism here allows you to capture the first of those values and completely ignore the rest, even if the next value is already on the very next tick. Have a look at this. We're going to simulate it. So I'm going to put a red value right here on a constant signal. Then I'm going to advance the game 1 tick. Then I'm going to change the signal to orange, advance it 1 tick again. Convert it to yellow. We advance 1 more tick, then light green, 1 more tick, finally green, and 1 more tick. And now we're going to cut the signal. And now in extreme slow motion, we're going to have a look at what's going on here. So, in the next tick, this red signal will move onto this wire right here, and it will trigger this transistor, which is connected to, in this case, the logo shape. Right here, you can put either a 1 or a shape value or a color value. It doesn't matter as long as it's any non-zero signal. But, for funsies, I decided to use the logo shape. So in the next step, that is going to trigger. All right, let's do that. There we go. Now we have the red on this wire, and it has triggered this transistor right here. The red signal moves into an artificial delay, which is set to 2 ticks. So 2 ticks later, the red color will come out there. Now, what this signal is going to do next is the following. It will move onto this blue wire. And because we have a transistor right here that, thanks to the NOT gate, is set to 1, we will create a constant feedback loop right here. In other words, after just 1 tick, this signal is going to be retained indefinitely. All right, so let's switch to the next tick. There we go. Now, this signal is retained on this constant loop right here. The addition of that signal to the wire will trigger the NOT gate right here, and it is connected to this transistor, which already has our shape loaded into it. But because this NOT gate is triggered, only during this tick will this code shape move through the transistor. As of the next tick, it will be shut off, right? So this is the only tick where we get a 1 on this wire. As of the next tick, it will be 0. This transistor will be shut, blah, blah, blah. The symbol then will move onto this wire and activate this transistor together with the first signal, the red signal, which is now ready to be output. So on the next tick, it will come out of the artificial delay, and also on the next tick, the transistor will be enabled, like so. Now we see that the orange is queued up, but thanks to this NOT gate and this transistor, our current tick is the only one where the special symbol we chose will be on this wire, meaning that only in this tick will the red color be allowed to pass. The next color, orange, which is queued up, it will be eaten up by the transistor. And then red will move onto this wire for 1 tick only, but is fed into a memory cell where the signal will be retained and the output will be constant. So here we go, 3, 2, 1. Red, orange gets eaten up, yellow gets eaten, light green gets eaten, green gets eaten, and there we go. Now the next thing we need to do, if we want to reset this system, the only thing we need to do is put a pulse on this line. This will cut the NOT gate right here for 1 tick only, and that will break the constant feedback loop we got right here. And then at the same time, simultaneously, I connected both a 1 and a 0, which will guarantee a conflict. And if you feed a conflicted wire into a memory cell, then that will reset that memory cell. So I push the button. We have a change detector right here to generate a 1 tick pulse. All right, and now we see that this NOT gate is triggered, the 1 and the 0 is triggered, and now on the next pulse, this feedback loop is broken right here. This line gets conflicted, and now on the next tick, this blue wire will be empty again, and the memory cell is cleared. Okay, let's repeat that. Now I'm gonna take green and advance 1 tick. Then I'm gonna take light green, advance 1 tick. We're gonna do the reverse as before. So now we got yellow, then we got orange, and finally we have red, and we advance 1 tick. So now the green is gonna get captured, and if I unpause the game, you will see that it happens within the blink of an eye. Here we go. Boom. That's how that works. Pretty sweet, right? And with that, my friends, we've got ourselves a wrap for this episode. And not only that, it's a wrap for the chapter about the decoder too. With this 5th and final part about the decoder under our belts, we can look at the rest of the machine. So I hope you're looking forward to it. I know I am. And my shapy friends, I've been Bins. Thank you for watching. Leave a comment, leave a like, blah, blah, blah. And let's meet again next episode. Ciao.